Good afternoon, everybody. I'm very happy to join you today in this second session of our Directed Energy Research Seminar. This session is being dedicated to laser photonics and optoelectronic applications. My name is Juan Coronel. I'm a laser researcher at the Directed Energy Research Center. I'm going to be with you during this session. I'm very happy to join you. And just some comments before starting our presentation. For the speakers that are not doing their talk, I just kindly ask them to keep the microphones muted. And for the attendees, we have a questions and answer button in the bottom of this window, so you can put your questions. We will dedicate 5 minutes after the talk of each speaker to have some scientific discussion. If the time is not enough, we will send the questions to the speakers to be answered in written form. We will have 6 speakers in this session. I'm very happy to introduce you today Professor Dai-Sik Kim. Professor Kim has a PhD in physics from the University of Berkeley. He has been a researcher in the AT&T Bell Labs and the Research Center for Laser in the Oklahoma State University. He has been distinguished physics professor at the Seoul National University and the Ulsan National Science and Technology in Korea. Now he's the director of the Center for Angstrom Scale Electromagnetism and member of the Korean Academy of Science and Technology. Welcome to our seminar, Professor Kim. The floor is yours. You can start your talk.
My journey towards zero-nanometer gap metamaterials. And thank you for this kind invitation, especially to Dr. Abdul Buchalka. I have known this guy for 30 years. We met 1990. So it seems like a long time ago. So today I'll talk about the extremely high aspect ratio nanogap, like this guy. So here it's enough for you to realize that this is a 1 Angstrom gap. Okay, it's a 1 Angstrom van der Waals gap, and the length along this way is 1 centimeter to 2 centimeters. So this aspect ratio between this gap width and the length, we are talking about 10 to the 8. And the thickness is about 50 nanometers. So this kind of sample I'll talk mainly. And also I'll talk about this terahertz nonlinearity and nanometer nonlinearity and Angstrom nonlinearity, etc. Okay. So I'll give you introduction, terahertz nanogaps, molecular cross-section enhancements, how to make 1 nanometer gaps. This is not easy, even with the focus ion beam or even lithography, I show how to do that. Nanogaps for microwaves, how to make Angstrom gaps, water inside the nanogap, and I'll summarize. Okay, so what is the smallest gap physically meaningful? It's clearly van der Waals gap. Here you see a cross-sectional image of copper film, graphene, and another copper film, cross-sectional. And you can see this white line, which shows the low electron density region, whose width is about 1.5 Angstrom each. So surrounding graphene ribbon, you see this van der Waals gap. So this is the ultimate gap. After this, you talk about bonding, covalent bonding, metallic bonding, and so on. So today we'll talk about terahertz, microwaves, and so on. You can see the spectral range here. Microwave, we'll talk about centimeter, terahertz, millimeter wave, some infrared, and also visible. Okay. So 12 years ago, I became a director of Center for Sub-Wavelength Optics. It's an inter-university Korean research center. And if you look at the x-axis is lambda wavelength, and y-axis is d. That's the dimension of whatever material you have. So you have terahertz, millimeter wave, microwave, micrometer visible, and here is a microwave and so on. And this is millimeter, micrometer, nanometer. Forgive me for this strange arrangement, okay, but it's logarithmic scale. And at that time, many researchers like terahertz, plasmonics, photonic crystal, metamaterials, plasmonics, and superlens, they were clusters along the line of lambda over 10, meaning that the feature size was about lambda over 10. Okay, if you have terahertz, you have larger feature size. If you have micrometer, you have wavelength, you have smaller size. Visible, you have even smaller size. Okay, and now we decide to go to lambda over 10,000 to sort of shrink the feature size very much and see what happens. So we envisioned terahertz plasmonics at millimeter wavelengths and nanometer feature size. And eventually we wanted to follow this line to go to visible and nanometer range along that line. At that time, we did not dare think about sub-nanometer spectroscopy. And this is sort of the skin depth region of good metal. And this is the Thomas Family length scale of good metal, which is Angstrom range. So, and we did some simulation and we got some idea about shrinking the gap to zero. So you can start from micrometer gap, 100 nanometer, 10 nanometer, 1 nanometer, 0.1 nanometer, okay? And it turns out that these gaps act as antennas. You can see the light becoming stronger and stronger when it passes through from the bottom to the top, okay? So it's a very good slot antenna actually. And how long will it continue? Can you make this gap 0.3 nanometer, for instance, and still get antenna action? Obviously, if your gap is as small as 0.3 nanometer, there will be some quantum effect, for instance. Okay, so essential physics here is, as you all know, vector Babinet's principle. If you have a gold wire, let's say very long gold wire, with electromagnetic wave impinging with the polarization along the wire, this can be considered as a good antenna. If you get Babinet analog of that, you get this slot in the middle and infinitely thin, infinitely good conductor plane. And these are equivalent. Babinet equivalent when you turn the polarization by 90 degrees. If you have magnetic field along the slit axis, this acts as a good slot antenna, meaning that polarization is actually perpendicular to the slot axis. And actually, this is a scattering microscopy of our Angstrom gap using graphene, which we'll show later. So this is another one example of sub-nanometer gap acting as very reasonably good antennas, okay? Now, how did we get here? Again, about 15 years ago, we are doing imaging of light transmission through slot antennas, and we realized experimentally that antenna cross-section is the same whether you have this wide rectangle or you have a narrow rectangle. You can use this narrow rectangle to amplify the light intensity at the middle, particularly for the electric field, okay? And there we got the inspiration that, okay, what if we go from 10 micron to 1 micron to 100 nanometer, 10 nanometer, go to zero. So this is a good imaging of this light concentration. So these were published in 2007, 2009, and so on. So again, this is the vector Babinet's principle that is working. Now, 2009, based upon this idea, we got this Nature Photonics article about tera field enhancement by metallic nanoslit operating beyond the skin depth limit. So there we show that is indeed light-induced current charge the capacitor, enhancing the electric field, by which diffraction theory said that there will be enormous transmission, much larger than what the gap width indicates. Okay, so experimentally we made a 70 nanometer gap with 5 millimeter length, which can be considered infinite because it's longer than any wavelengths we used. Okay, so from experimentally by diffraction theory and transmission data, we could get field enhancement of about 1000, but the field enhancement decreases with increasing frequency, following 1 over f. So this is a famous 1 over f for constant current charging the capacitor, because you have less time to charge the capacitor when you have high frequency. Okay, so that's sort of also an equivalent phenomenon at the microslit. So micro and nano go very well together. And what's interesting here is that electric field becomes enhanced by a factor of 1000, but magnetic field stays almost the same. If you get the product between these two, you get point vector enhancement. Okay, at that time, the smallest gap we thought about, theoretically even, was 20 nanometer. And I will show you how to go to 0.3 nanometer today. Okay, so you can see that we went from round about 10 line to round about 10,000 line for terahertz range. And we'll show you one functionality of this, which is very striking. I'll show you how these terahertz nanogaps can enhance quantum mechanical cross-section of molecules by more than factor of 1000. So it makes molecule appear much, much bigger than without nanogap. Okay, so this was published in 2013, Nano Letters. What we did was we have this single slot antenna, and we put this famous plastic explosive RDX molecule. And basically, we saw that the cross-section is very much enhanced, so that this alpha, which is the absorption coefficient, which was below 100 wave number for bulk. When you go to the slot antenna, everything becomes much more sensitive. You can put a lot less RDX onto the slot, and you get lots of detection action, unlike in bulk. So you can see that the cross-section, alpha, absorption cross-section, go from, remember, below 100 wave number to over 100,000 wave number, which is as good as silicon or ultraviolet. So this is a semiconductor-like absorption coefficient for terahertz. Semiconductor ultraviolet-like. So it's very much enhanced. So why is this happening? We did all the math and quantum mechanical calculation of Fermi, golden rule, etc. And what we found was that basically electric field gets enhanced a lot inside the slot antenna, which means the absorption, because absorption goes at this scale, gets enhanced by a million times, but the Poynting vector is not enhanced as much. So you have energy imbalance. You have less energy comes in, but it gets enormous absorption, so that you basically have very big cross section. So the molecule which look like this, barely visible without the antenna, becomes very much visible with antenna like that. So molecules appear bigger. All right. So what's interesting is this physics. The physics is that if you enhance electric field like a slot antenna, your molecule will appear larger. If you were to ever enhance magnetic field, the molecule will appear smaller. Okay? So there's a very interesting electromagnetic effect in terms of cross section. But it will be good for magnetic molecule, for instance. Okay, so this was 13. Now how to make 1 nanometer gaps. So we use basically essentially side-wall lithography. Okay, we fully take advantage of thin film technology to make 1 nanometer gaps. So what you do, you just have one of the mere garden variety photolithography, 100 micrometer, 100 nanometer thickness, the feature size, and so on. And then we do ALD, atomic layer deposition of Al2O3 in this case, but any other oxide will do. Now, when people do ALD, they are concerned about the top surface. But it actually conform only coat the side wall as well. So you have a potential dielectric gap here. That is only defined by the thickness of the sample, thickness of the film. So you get second deposition, and you take the top out. Then you get this beautiful rings of nanometer gaps, and you can see that on the visible microscopy. So this is published in Nature Communication 2013. You can go to 1 nanometer indeed. This is a cross-sectional image. So you don't have to use the same material for first deposition and second deposition. You can use silver and gold, for instance, and so on. Okay. And indeed, even 1 nanometer gap is a good antenna. It supports enhanced transmission, field enhancement of up to 10,000. Very nice slot antenna. Okay, so this was Nature Communication 2013. And we, for instance, apply this to vanadium dioxide. We use VO2 as a substrate, and we have this nano slot antenna on top. And you can see that you can do some kind of transition engineering. You can change your parent transition temperature. And it's not really material property that is changing. It's the sensitivity of the whole thing changing. So that even the Boltzmann tail before the metal insulated transition makes the purest transition. So this is a pseudo transition, but it can be very useful still in the terahertz range. So this was published in Nanoletters 2015. Now, we are doing it terahertz. Let's go microwave. I mean, microwave has more application at the moment. So, what do we do? We apply the same principle. You can make slot antenna with micrometer feature size, and you'll get transmission very much enhanced. You can do also etching lithography without peeling. For large area, for high reproducibility, high throughput, you can do this. And this is published in 2015 as well. And basically, you can get these beautiful nano antennas geared for microwaves. So this is microwave nano. And you can see the whole terahertz to microwave spectrum. So we combine terahertz time domain spectroscopy with the network analyzer to get this spectrum. Okay. Another thing we did recently, it was a nano letter last year, is strongly localized ohmic absorption of terahertz radiation in nanoslot antennas. We basically began to etch antennas and see what happened to the absorption. We performed both reflection and transmission. And you can see these nanoslot antennas had gigantic absorption, up to 50 to 70%, which is very unusual. This will never happen for microgap antennas. You have absorption is almost zero because that's a perfect conductor. It's not the case when you have nano antennas. So this is a picture of very macroscopic scale. You can see that this is like a few millimeter. This is also few millimeter. This green line is basically laser transmission, but it shows how this ring antenna designed for microwave look to you. And you can do multi-wavelength spectroscopy here. So that's very nice. So you can do infrared, terahertz, and microwave together. So this was published in ACS Photonics 2016. So we basically went full nano, not just 100 nano. We went full nano at terahertz. Can you go even further? Can you go sub-nano? Okay? Indeed. We'll do that. We'll keep going until we go to 0 nanometer, okay? So how to make Angstrom gas? We know how to make nano gaps, Angstrom gas. Why not? So basically use copper. Copper is a catalyst for graphene growth under the right condition. You coat it with single layer graphene like that. Your second layer copper, and you tape it out, and you have Angstrom gap, like 2 Angstrom gaps. When you see the cross section, surrounding graphene ribbon. Okay. So here's a top view of SEM image. You saw the dark field microscope image before. And this was published in Physical Review Letter 2015 as a cover. We call this Angstrom gap lithography. We still have a long way to go. Okay, so now a little bit of rectification. It's if you use energy harvesting application at high density, you all know rectification. You have sinusoidal wave, you end up with DC. It's very useful for power transformation and so on. Every transformer has this rectification. Now, what we show is that this ring of nanogap is a rectifier of terahertz beam at high intensity. And it matters whether we have inversion symmetry like this rectangle or no inversion symmetry like this triangle. And indeed, experimentally, we show that this terahertz beam, which is minus plus, minus plus, minus plus, minus becomes plus, 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 plus. It's a full rectification, okay? And that was published in 2018 in Nature Communication. And we show that this is such much better rectifier than this because of lack of inversion symmetry. So the macroscopic geometry enters how the overall ternary efficiency goes. So again, there's rectification. Okay, a little bit of chemistry and water. These nanogaps do not like water because surface tension typically. But we managed to insert water inside the nanogap by a very clever combination of etching plus diluting of the etchant using water. So this was a very nice effort. And you can see that the IL-203 is fully etched. There's only air here, okay? And you can insert water afterwards. So you can see this empty gap, water on top, water fill. You can distinguish this. So this was in Advanced Optical Material 2018. So last 12 years, we have went from 50 microns to 70 nanometer to 1 nanometer to 1.5 angstrom. So this was quite a bit of a journey. So now we are interested in making it really zero. Along the way, we found some applications and have built some foundations for the future research. And we have written some nice review articles recently, Advanced Optical Material, Journal of Applied Physics, Nanophotonics, and so on. So this is acknowledgement. Recently, I moved from Seoul National University to UNIST. Now this lab is pretty much filled, okay? And we have 5 distinguished professors together to form a very strong nanophotonics group, Quantum Photonics Institute. And UNIST is a relatively new science-oriented university. It's along the line of KAIST, GIST, DGIST, UNIST. These are 4 science and engineering oriented universities in Korea. And it's close to Japan. So I moved from Seoul to basically Ulsan here. And you have very good infrastructure like nano fabrication and good student support and so on. So we want to go to picometer gaps and so on. So let me just spend 1 minute for research opportunities so that maybe we can collaborate. We can send our students there. We can send your students and postdoc. We have excellent support for students. Full support, no tuition. That's important. So sub-nanometer phenomena we are interested. Metamaterials, quantum metamaterial, phase transition metamaterial, we configure metamaterial. We are very much pursuing that. Molecular reactions using tunable gaps. That's one of our vision. Multifunctional acoustic devices, band gap changing metamaterials, zero-nanometer gap platform. Okay, so maybe I can summarize. So terror, gentle, van der Waals, Angstrom gap regime. So we have a dense infinite nanogap is a very good platform for micro to ultraviolet. Nanogaps provide new functionalities, not only polarizer but all kinds of other things. And nano Angstrom gaps for material science, device physics, macroscopic quantum phenomena are some of our interest. And zero nanometer gap, we are pursuing it very much. Okay, thank you very much for listening. Oh.
Thank you, Professor Kim, for your talk. It's a very interesting subject. Now the floor is open for questions. Okay, I have one question regarding this very interesting concepts you have presented to us during this talk. And it's regarding these nanogap antennas. I see they are high performing in microwave frequencies. This will lead to the reduction of size of in several applications. Have you already tested these antennas in, for example, telecommunication devices or other kind of technology could be useful for your research purposes?
That's a very good question. We are vigorously pursuing that, writing patents and so on. We are very close to a working device. I cannot tell you more, but we are very much into that.
Okay.
Like very much into microwave shielding and so on. Those are some of the things you can do right away. Thank you.
Oh, thank you. Any other question?
I just want to ask you, Dr. Kim, about the different shape of antennas. Did you investigate into that besides the dipole antenna?
Different antenna shape, yeah.
Different shapes, you know.
Yeah, we have you have like a triangular antenna,
Okay.
which has inversion symmetry least,
Yes.
and that has completely different nonlinearity. And you have rectangle, square, star shape, and so on. We're also doing chiral shapes,
Okay.
chirality. So you can have all kinds of different shapes. So we are playing with that, definitely. Yes. Not just squares or rectangles. Yes. Thank you.
Did you try it on design for specific detectors?
Yeah, we are actually, we can also make like bow tie type.
Mm-hmm.
And we are collaborating on how to make good bolometers out of that.
Okay.
Yeah. So we are doing many things. Thank you.
Okay. Thanks again, Professor Kim, for your very interesting talk.